All right, here we are. Let's wrap up the stoichiometry. This is everything you could ever be asked to do with stoichiometry calculations. If you can do this, you are in a great place. So we got to think of this as a very methodical process. We have 400 grams of hydrogen gas added to 3,500 grams of nitrogen gas, and 1,040 grams of ammonia were formed. First, we want to know the percent yield for this reaction, and then how many grams of the excess reactant will be left over. Okay, so number one, I can't do any kind of stoichiometry without a balanced equation. We need the balanced equation. This is one that we've looked at in the past. Hydrogen gas is diatomic, plus nitrogen gas, which is also diatomic, producing ammonia, which is NH3. I'd give you that if it weren't given in the problem. We need to balance. The hydrogens are not balanced. I see 3 and 2, so we're going to go for 6. 3 times 2 is 6. 2 times 3 is 6. And what do you know? 2 nitrogen, 2 nitrogen. Perfect. All right, so part 1, get the balanced equation. Eventually, I want to use that 3-to-1 ratio between the hydrogen and the nitrogen to figure out the limiting and the excess. If we want to calculate the percent yield is actual over theoretical, which the actual usually comes from lab data, or in this case, they're going to tell us. This right here, this 1,040 grams of ammonia that were formed, that's my actual yield. Actual yield. On paper in a problem, they have to tell you how much was really collected. Okay, cool. So we just need to calculate the theoretical. The theoretical, which is calculated by using the limiting reactant. Oh, brother, we got a lot of work to do. Okay, so before I can do the limiting reactant, I cannot work with those masses. The original amount of hydrogen and nitrogen were given in grams. We got to get those out of grams into moles. All right, so one of them is 400 grams of hydrogen gas, which is diatomic, and the other is, oh brother, 3,500 grams of nitrogen gas. So to both, we'll set up kind of a similar proportion. We want to cancel grams, get her in moles. 1 mole has the mass on the periodic table. Since they're both diatomic, we'll multiply by 2. All right, so 400 divided by 2.02. I'm good with 198.0 moles of hydrogen. Then we do the same with our nitrogen. Cancel grams of nitrogen, switch her to moles of nitrogen. Okay, so 1 mole has the mass on the periodic table multiplied by 2 because we're diatomic. All right, so 3,500 divided by 28.02. 124.9 moles of nitrogen. These amounts here are what I have. This is what I really have to work with. I just took the original masses and turned them into moles. That's still what I have. So now we need to figure out the limiting reactant. Okay, so sometimes the ratio is really easy and the numbers are kind of obvious. Sometimes maybe not. So you have a few options. Option 1, maybe you just want to calculate the limiting reactant. Maybe that's more your style. If that's the case, you pick one and you switch it to moles of the other. Okay, so it doesn't matter which. I usually just pick whatever comes first. Let's say I pick the moles of hydrogen. And I do a little calculation to figure out how much nitrogen I would need. It's just a little mole switch. Cancel moles of what you pick and switch it to moles of the other reactant. We're trying to find the limiting reactant. It is a 1:3 ratio according to my balanced equation. And then I just plug this in. 198 divided by 3 is about 66 moles of nitrogen. That's the amount that I need. Have versus need. Okay, so we make a little comparison. You have to make sure that you're comparing the right substance. This is nitrogen to nitrogen. I need about 66 moles, but I have almost 125. I have like almost twice as much nitrogen as I need. There is no doubt that in my mind that the nitrogen becomes my excess reactant. So by process of elimination, I'm expecting the hydrogen to be my limiting. And you could have calculated the amount of hydrogen needed. Maybe you would have started with the nitrogen and turned it into hydrogen. That would have been fine. Maybe you even did this by inspection. So a 1:3 ratio is not like super crazy. And these masses, I should say moles, are numbers that I can kind of manipulate in my head. I need 3 times as much hydrogen versus my nitrogen. I need 3 times as much hydrogen. So it's like saying, if I were to take this nitrogen and multiply by 3, that's about the amount of hydrogen that I need. So I would need approximately, I mean, if I just estimate, like, okay, maybe that's about like 125 moles of nitrogen times 3. Oh, brother, that'd be like 375-ish moles of hydrogen. Whoa! I don't have that. I got like about half of it. I got about 200. But I definitely don't have 375-ish. That's my limiting reactant. So you could have figured out limiting reactant here just by estimation. It's a pretty easy ratio, 1:3, and the numbers are pretty obvious. Like, it's not even close. Maybe you could even do this kind of in your head too, or at least estimate. If I were to take my hydrogen, then I'd be dividing by 3 to figure out the amount of nitrogen needed. And so again, maybe you just estimate it. I mean, we actually calculated it in red, but we needed 66 moles of nitrogen. And we had way more. But I mean, that 66, that's never going to be used in my other calculations. That's just telling me how much of the excess gets used, the amount of excess that's needed. I could kind of estimate. I could estimate that about 200 divided by 3 is way less than 125. I could tell you that much. So that 125 will be way more than what I need. And so you could do a calculation kind of like what we did in red, or maybe you just kind of estimate, and then you write a sentence. When you see this on a test or quiz, it's going to say, justify your answer. What's the limiting reactant? Justify your answer. So then I know that you just didn't guess correctly. It would be fine to say that the limiting reactant is hydrogen because I need approximately 375 moles, and I don't have that. That's enough justification. Okay, so when you're doing these problems, even though technically they're not asking for it here, the first thing I need is that balanced equation. I gotta have the balanced equation. Because I need to know the ratios. Second thing I need to do, calculate the limiting reactant. Or I could say determine the limiting reactant. Because the limiting reactant is the one that determines the theoretical yield. It determines how much product will actually be formed. Cool. Okay, so if I look at my balanced equation, hydrogen is my limiting, and nitrogen is my excess. So it'll be the hydrogen that determines how much ammonia can be produced. Okay, so now we can do the theoretical yield part. Theoretical yield. We're going to start with the amount of limiting reactant that we have, which we already took that 400 grams and turned it into moles. So we could start with the 198 moles of hydrogen. It's my limiting reactant. We'd be switching it to moles anyway, so since we already did that, let's just take a little shortcut. Since I'm in moles, now I can cancel moles of hydrogen and switch it to moles of my product, ammonia, and H3. The ratio is 2 to 3. I find joy in crossing these off. So now I'm at moles of ammonia, which I'm trying to calculate the theoretical yield, and the actual is given in grams, so we might as well bring this one back to grams. All right, I'm going to cancel moles of ammonia and bring it to grams. 1 mole has the mass on a periodic table. Nitrogen plus 3 hydrogen. 17.04 is good. Moles are out, and we can plug this in. Okay, so 198 times 2 divided by 3 times 17.04. Woo! 2,249 grams of ammonia. That's a lot. That's my theoretical yield. Okay, so first we had to calculate the limiting reactant. Then we had to calculate the theoretical yield. So that now we can finally answer some of these questions. They want the percent yield for the reaction. Percent yield is actual over theoretical. Percent yield, actual over theoretical, times 100 to get a percentage. The actual was given up in the problem. It's at 1,040 grams divided by 2,249 grams. That's not very good. Times 100. I don't know, like 3 or 4 figures maybe. 36.24%. Interesting. They lost more than half their product. Now we could calculate the percent yield. But this is a reaction that deals with a bunch of gases, and that is kind of typical. It's hard to really contain a gas when it's produced. All right, we finally answered a question. Percent yield, we got it. But we had to go through all of this other stuff to get there. We needed the balanced equation. We needed to determine the limiting reactant so that we could calculate the theoretical yield, which then we could use to get the percent yield. We were given the actual. That's a lot of work. And we're not done. Next, up on top it says how many grams of the excess reactant will be left over? Well, first we have to figure out how much of the excess reactant gets used. It's actually going to look very similar to this calculation right here. We're going to use our limiting reactant. It runs the show. When the limiting reactant is used up, the reaction stops. So we don't make any more product, and we don't use any more of the excess reactant. Here's the stoichiometry we're going to run. We're going to use the limiting reactant to determine the amount of nitrogen, the excess, that gets used or reacted. Okay, so it's going to look a lot like how we calculated the theoretical yield. We'll start with our limiting, the amount that we have in moles. Hydrogen was my limiting. But this time, instead of switching it to the product, we'll switch to the excess reactant. We'll cancel moles of hydrogen, switch it to moles of nitrogen. It was a 1-to-3 ratio. So this guy right here is our excess. Cool. Moles of hydrogen are gone. And now I can bring that to grams of the excess used. So it looks really similar to what we did up on top. We'll cancel moles of nitrogen, switch it to grams of nitrogen. 1 mole of diatomic nitrogen is 28.02 grams. Moles are gone. Plug her in. 198 divided by 3 times 28.02 is, oh boy, maybe like 1,849 grams of nitrogen. And again, that's the amount of nitrogen used, reacted. Sometimes they might use the word consumed. First, we had to figure out the amount of the excess used so that we can figure out the amount left over. That's just a subtraction. So we go back up to the original problem to find the amount of nitrogen that we had. Oh, brother. It was that 3,500. That's the amount that we have. And then we can subtract the amount that gets used. 1,849 grams of nitrogen used, reacted, consumed. The difference, that's a comma, 1,651 grams of nitrogen excess. Woo! That's a lot of work. That's impressive. That will impress your friends. So finally, our last calculation. We had to calculate the amount of the excess used and left over, or excess. That's just the subtraction. But before we could subtract, we had to figure out the amount of the excess that got used or reacted. Now we just subtract from what we had. Now you can do this in moles. So for example, if I look way back up here, I mean this is, whoopsie, not that one. This guy, this 124.9, that's the amount of nitrogen that we have. That's the original amount that I have. We just switched it from grams to moles. If you stop right here, that's the amount of nitrogen that gets reacted. So that's the 198 divided by 3, which is, I think, like 66. So if you want, you could also do this subtraction in moles. You could say 124.9 moles is what I have, minus this 66 that I need. It was only 66 moles that got reacted or used. The difference then would be the amount of excess nitrogen in moles, which then maybe we would just change back to grams. But it doesn't matter if you do this subtraction in grams or moles. You just might have to switch it to grams at some point. So then I just brought this guy back to grams. Whoa, that's some good stuff. These are like multi-point problems. There's a lot going on. And it's not the math that's difficult. I know you can do the math. It's just multiplying and dividing. But you got to know what's going on. You have to understand the chemistry to know like what numbers to even put on paper. This will require practice. But if there's things here which, I mean, you're looking at now and you're saying, I have no clue where these numbers are coming from, then it's time for some stoichiometry intervention. At this point, I would suggest pausing the video and trying the last one. See how far you can get. A lot of this is just some stoichiometry, just limiting reactant stuff. I mean, think of this as, a typical limiting reactant problem. We need the balanced equation. We got to get grams into moles so we can look at the ratio from the equation and determine limiting and excess. Use the limiting to calculate the amount of product formed. I mean, the only new part is maybe this percent yield. But the rest is kind of similar to what we've done in the past. So see how smart you've gotten on the last couple of weeks. Pause right here, try the last one, then bring it back, and we'll go through it. Okay, let's see how far you got. Did you cheat? Did you have to bring it back? Did you get stuck? If you did, it's okay. All right, first thing we needed, balanced equation. So when I read this problem, I see 3 numerical values and I don't really care until I figure out the reaction. I'm just looking for the reactants and products. When 200 grams of silver 1 nitrate reacted with 200 grams of sodium phosphate, 160 grams of silver 1 phosphate precipitate were collected. What is the percent yield and how many grams of the excess were left over? Okay, so here's a bunch of ionic formulas. It's a double replacement. Check to make sure that you had those formulas written correctly. You will be given polyatomic ions. If you're doing a test or a quiz, you will have those polyatomics. Now you kind of got to keep them handy because you'll need to look them up a lot. Maybe you memorized them. But check first to make sure your formulas are correct and your ratios are correct. One of the products is that silver 1 phosphate. Cool. All right, once I got the equation, now I'm going to try to figure out the limiting and the excess. So we've got 200 grams of each reactant, but I can't compare them in grams, so we need to get them into moles. Which, look at this, kind of wild. They're almost the same. Their molar masses end up being really similar. However, you need 3 times as much silver nitrate. Here's one that I could totally do by inspection. If you take this sodium phosphate, you need 3 times as much silver nitrate. You would need like what? 3.66 moles of silver nitrate? Just by inspection and estimation. I don't have that. Limiting. Ah, cool. Which actually in real life, silver compounds are often limiting reactants. They're super expensive. So you wouldn't want to use something really expensive as your excess reactant, because in the end, what's excess just gets dumped down the drain. It's not chemically reacted. So if you have something that's really rare or really expensive, that's going to be your limiting reactant. You want to make sure that you completely use up all of that expensive reactant. Sodium phosphate, I'll throw a little of that down the drain. That's cheap. Now you could also do a calculation. So for example, I just randomly picked one reactant. I usually just pick whatever comes first. And now you're actually plugging it in your calculator. If I picked the silver nitrate, a third of that should be my moles of sodium phosphate, which again, I can kind of estimate. And this is about 1 divided by 3 is about like 0.3 something, which I can tell you right now, I've got way more than that. The sodium phosphate is your excess. Cool. All that work just to figure out the limiting reactant so I knew which reactant to use in calculating the theoretical yield. All right, so here's my theoretical yield. I start with the amount of limiting reactant that I have. You might as well use it in moles since it's already in moles. Then we can use the ratio in the balanced equation to go from silver nitrate to the product, silver phosphate, and then moles to grams. Boom, there she is. This guy right here is my theoretical yield, this 165. Which then I can use to figure out my percent yield. This one was a lot better than the last one, huh? They tell you in the problem that 160 grams were formed or collected, but we should have gotten 165, which in reality, this is really good data. Usually in the lab, if you're within like 20%, plus or minus 20%, that's good data to me. This one's like 97% yield. That's good. First part of the question, check. We got the yield. The second part wanted to know how much of the excess is left over. How much of the excess is unreacted? So these two blue calculations look very similar. The first one, we took the limiting reactant and we turned it into the product. This one, we're going to use our limiting reactant and turn it into our excess. And then I just went one step further and went back to grams. This 64.5 grams of sodium phosphate is the amount that gets used or reacted, which then you can just subtract from the original amount that we had to get the amount excess or left over. You got enough sodium phosphate to run this thing like twice. But we run out of silver nitrate. 165.5 grams left over. And again, you could have done this subtraction in moles, because essentially, here's the moles that I have. Here's the moles that I need. If you subtract those, it tells you the moles left over, the moles excess, which then you can just go moles to grams. You get the same answer either way. There she is. Are you on the right track? It's a lot. This is some of the most intricate chemistry that you will do all year long. Your friends will be so impressed. So again, this takes practice, which is exactly what we're going to do now, until we reach perfection with this limiting reactant and percent yield stuff. But it's great. Once you catch on, you will love it.